In this course, we chose to teach relational logic, which is different from a more commonly taught logic called first-order logic. The two logics share the same syntax, but have different semantics. That is, the same set of sentences can mean different things in the two logics. In this segment, we discuss the differences between the two logics and give some reasons as to why we chose to teach relational logic. In relational logic, possible worlds are considered over the ground terms in the language. For example, over the language consisting of object constants A, B, and the unary relation P, there are exactly 4 possible worlds. One where P is false of both A and B, one where P is false of A but true of B, one where P is false of B but true of A, and finally one where P is true of both A and B. In first-order logic, possible worlds are not constructed over the ground terms. Instead, each world defines its own set of objects. Objects like the number 1, the real number pi, a triangle, a square, or even Mike Genesareth. And the ground terms in a language actually refer to the objects in the world. Let's see some examples. Over the same language, A, B, and P, the possible worlds in first-order logic include one where we have the objects triangle and square, A referring to triangle, B referring to square, and P being true for triangle and square. Main difference here being, one, we specify the set of objects in the world, and two, where P is defined over the objects in the world rather than the terms in the language. Now, another possible world is where we have a single object triangle in the world. A and B both refer to triangle, and P being true for triangle. We can also have infinitely many objects. For example, let's let the set of objects be the real numbers. We can have A referring to the real number 1 and B referring to the real number pi. We can, for example, have P being true for all the rational numbers and false for the irrational numbers. And you can see that there are infinitely many possible worlds. So you can see that by comparison, relational logic has very simple semantic. Each world is a truth assignment over the ground sentences in the language. It's just like a database. First-order logic semantic, which we previewed very quickly here, is much more difficult to define and to understand. And for those interested, the Wikipedia page is a good place to start. Relational logic is also more precise in describing worlds. That is, it can tell you more about how exactly a world is. Over the language, arrow being A, B, and P, let's consider the set of sentences sigma, saying that P holds of A and P holds of B. Now, in relational logic, there is exactly one world that satisfies sigma. That is P being true of everything, A and B. But in first-order logic, there are many different worlds satisfying sigma. One, for example, where we have the object triangle, both A and B referring to the triangle, and P being true for triangle. Another one where we have the objects triangle and square, A referring to triangle, B referring to square, and P being true for triangle and square. A third one where the objects are triangle, square, and smiley face. A and B still refer to triangle and square respectively. P remains true for triangle and square, but it is false for smiley face. And there are many, many more possible worlds in first-order logic that satisfy sigma. So what we're seeing is that the same description sigma that under relational logic precisely defined one world actually emits many different possible worlds in first order logic. A practical consequence is that in relational logic, we can finitely define the system of natural numbers with addition and multiplication. And this is impossible to do in first order logic. Whenever you write down a finite set of sentences that in first order logic emits the system of natural numbers, it is also going to emit other systems that differ in substantial ways. First order logic is also weaker in deductive power than relational logic. That is, from the same set of sentences, more conclusions are entailed under relational logic. Let's see an example. From the set of sentences P of A, P of B, we saw earlier that there is exactly one world in relational logic that satisfies the set of sentences. In that world, P is true of everything. So in relational logic, it is entailed that for all x, P of x. The same does not hold in first order logic. We saw that there is a world in first order logic satisfying P of A, P of B, but P is not true of everything in the world. So we cannot entail for all x, P of x under first order logic. We saw that relational logic is more powerful than first order logic in describing a world. But what about mechanically proving consequences? We know the fit system without domain closure and induction is sound and complete for first order logic. That means under the system we'll call Fitch minus, a sentence is provable under Fitch minus if and only if the sentence is a consequence, is entailed under first order logic. What about for relational logic? We know that the Fitch system with domain closure and induction is sound for relational logic. That is, if a sentence is provable under the system, then it is an entailed conclusion under relational logic. But the system is not complete. So there are examples where you have a sentence that is entailed under relational logic, but is not provable with this proof system. That seems like a big disadvantage, but it isn't actually. Because the Fitch system, even though it doesn't prove everything that is entailed under relational logic, it proves everything that first order logic entails, and in fact it proves more. So if we were comparing proof system to proof system, we still have greater power in relational logic. In some sense, relational logic can do everything that first order logic can do, in the sense that we can actually emulate first order logic using relational logic. Let me tell you what I mean by that. Let's consider any language arrow with at least one object constant. For example, arrow equals P. Let's define arrow plus as the extended language where we augment the original language arrow by a new function constant n. So arrow plus in this case would be a, object constant a, function constant n in the relation P. Now, for any set of sentences sigma and a sentence phi over the original language arrow, we have the result that sigma entails phi in first order logic if and only if sigma entails phi in relational logic over this extended language arrow plus. We've seen that relational logic has very simple semantic, it is more precise in describing worlds, and it has a more powerful proof system. It can even emulate first-order logic when you want to. First-order logic has a very important place in mathematics and philosophy, and I would certainly encourage you to study first-order logic as you continue your education in logic. But for all the reasons mentioned in the last slide, relational logic is a better logic for common use and a better choice for a first course in symbolic logic.